For you. All right. Several years back, a company called SoftRaid was acquired by OWC. And Tim, who has spoken at a number of MacTech conferences over the years, actually, I think last year you revealed a product that was conceived at a MacTech conference conversation like 2 years prior or something like that.
Yes.
So whatever it is that you want to ship like 2 years from now, now's your time to get that in, with Tim. But we were talking about what could he talk about this year on it. And of course, APFS was the discussion of choice. And there's the certain amount of pain that goes along with APFS or could go along with APFS. And the idea was, how do we avoid some of the pitfalls? How do we get some more performance out of it? How do we, just really make the most of what we have with APFS, since Apple hasn't really fully baked everything in the way that we would like with all the third-party solutions that were there. So I can imagine there's only a few people in the world that could do this talk well. How about a very, very warm welcome for Tim Standing?
Thank you. Thank you. So I just have to start my timer so that Neil doesn't have to run up and shoot me off the stage. What's that? Oh, white napkin anyway. Okay, good. So the talk is a little bit different than what Neil suggested or how he described it. I've always come to these conferences and I talk to a lot of people. You guys manage thousands of computers, and I always hear about your problems and try and come up with new solutions. And I see my part of this whole thing as giving you sort of the developer's view on what I see is going on. So this is going to be a deep dive into APFS. It's going to give you some information about how APFS works and why, or how that has direct implications on, I don't have slides.
So that's what they're saying. That's what they're saying. You keep talking.
I keep talking. Okay, so can I stop my timer? I have my own laptop if you want.
You've been officially blessed.
Okay.
For extra time.
Okay. So anyway, so I look at APFS. I'm really excited about it. I love new tech. The new iMac is the new Mac Mini is the first computer I've seen from Apple in 6 years that I'm like, I want to go spend my own money on it. It's really cool. I change my monitors every 10 years. I change my computers every 4. This idea of buying an iMac Pro where I have to throw out the monitor in 4 years is sort of crazy. So I prefer to buy a really good monitor and a really good computer and then replace the computer every 4 years. So anyway, going back to APFS, I was really excited when I heard about it. I was really excited when Apple started talking about ZFS back in 2006. That never came to be. I'm actually glad now that it didn't, because ZFS really requires the ECC RAM to be usable, and we still don't have video, huh? Well, I can hold my laptop up and you can see it, but...
No.
Okay.
What did you say? It's around the desert again. That's not what I thought you said.
Okay, great. Fabulous, thank you. Can I just use the down arrow here? Okay, good. Let's keep it low tech. Okay, here we go. I am, as Neil said, SoftRaid, the company, was bought by OWC. They were coming out with this new line of Thunderbolt storage devices. I called them and I said, hey, you might want to license SoftRaid. We're just about to release RAID 5 and RAID 4. It would be perfect for your JBOD solution, because they didn't have hardware RAID in their boxes. And Larry, the owner of the company, who I love him because he's always thinking outside the box, his first answer was, can I get you to give me a 6-month exclusive? And then I flew out to Austin, gave him a demo, showed him the email notification we have built in, showed him working with cell phones with SMS messaging, and he, as soon as I got on the plane, when I got back, he said, well, how about if I buy your company? And within 3 weeks, we had a deal sort of etched out, and I've been working with them ever since. I'm really Still love working with them. They've given me a lot of resources that I didn't have before to file patents and do other things. We found a company that had actually reverse engineered soft-RAID on Windows, so that you can mount a soft-RAID volume on a Windows machine. And I persuaded Larry last year to go and investigate whether we could purchase that company, and we did. And they're now doing soft-RAID for Windows, which should ship in January. They have 3 engineers working on it, and it looks killer. I think it's going to be great. People have been asking me for soft-RAID for Windows for I don't know how many years, and it's great to see it finally coming out. So I'm going to start by doing a little quick review of last year's conference here, my talk here. Particularly, I want to talk about copy on write and how we're going to contrast copying files in HFS versus copying files with APFS. So with the example file I'm going to use is a 10 gig file. It's a movie file. It's got 2 what we call extents, which are contiguous parts of the volume on disk. When we copy it, cha-chunk, cha-chunk, you hear the disk heads going back and forth. It takes quite a while to do the 10 gig copy. What you're doing is you're actually reading the data from the first file and writing it to a separate part of the disk. So you're going to take up twice as much space, et cetera, et cetera. Then when you go and do an edit on your original file, you're going to write in place. In this case, we're editing 4 places on the original file. We're going to write over the original data. No surprises. Apple's been, this is sort of the way it's been for 30 years. So with APFS, we start off with the same thing, but what happens when we copy a file is we actually get pointers from both the old original file and the copy. The file structures, the metadata points to the exact same parts of the disk. So now you have, it's like 2 people sharing the same phone number almost. It's a little crazy because you think, oh my God, what's going to happen when I want to go and write to one of those files? Well, what happens is when you write to one of those files, the file system goes, hey, this little section is no longer the same. I need to go find some space on the disk for the part that's different and write to it. So in this case, we've got 4 blocks we're writing. They're discontiguous. It's the original file you're writing to, so when you're reading the original file, you're going to read the common stuff until you get to the first edit. Then the head's going to go swinging over and read that new information. Then it's going to come back and read the common information, swing over, read the new information. At the end of this talk last year, I said to myself, this is really crazy. Apple should do something about this because it's going to kill performance on hard disks. And I wrote a bug report, and Apple sort of said, yeah, it works as designed. You don't know what you're talking about. And then I wrote another bug report in January, and I got the same response. And I went to the developer conference this year, and I said, I talked to 2 of the actual people writing the APFS code. And I said, this is a problem. And they said, no, we've added something in 10.14 that actually makes the performance much better on small files. 10 or 20 megabyte files. It's not an issue anymore. You're going to love it. I said, oh, great. Well, what about larger files? And then one of them said, we have this technology already in there where we can turn off copy on write. And I said, well, why don't you just expose it so that we can make use of it? And I knew nothing was going to happen with Apple. Nothing happens unless you file a bug report, so I filed another bug report. But before I did that, I thought to myself, these bug reports, I filed, it's like they've got 3 levels of triage before it actually hits an engineer. And during that triage process, the people are sort of going through those bug reports so fast that they're really not paying attention. So what I thought I would do is I'd actually document how much slower it was. And I'm no Python whiz, but thanks to Greg Nagel, who I keep saying thank you to Greg Nagel. He's the one who taught me Python at a MacTech conference, 4 years ago? And I've been using Python and loving it ever since. And so I whipped up my Python chops and wrote this tool Python script that would basically fragment a file. So you start the thing, it puts up a prompt saying, go and duplicate this file in the Finder, and then it just starts going and fragmenting the file, unmounting the volume, remounting the volume, and timing the amount of time it takes to read the entire file. Now, obviously, we need to unmount and remount to make sure there's nothing in cache. And we do that. So I do this 10 times. For every iteration, I do 1,000 fragments. So at the end, I've got a file with 10,000 fragments in it. As a quick note, I'm not using for these tests really slow hardware. I'm using a 4-drive, this is our Thunderbird product, 4 drives on Thunderbolt 3 as a RAID 0. So we're seeing roughly 800 megabytes a second read and write. For solid state storage, I'm using our Thunderblade product, which is a fanless 4 M2 blades in it. Again, striped together, we're getting about 2 gigs a second on that. So just as a starting point, I ran this test on HFS volume, and as you expect, since we're doing the discontiguous writes, we're doing them right over the original data, there should be no effect, and there isn't. It's the same speed all the way across the board. So if I do that instead on APFS volume, this is what I see. This is a 10 gig volume. It goes up roughly 15 seconds for every 1,000 discontiguous writes. I was an experimental biologist or biochemist for a long time, and so I always do a back of the, does this data make sense? Does it actually gel? So I look at this number and I say 15 seconds, 1,000 writes. So I divide by 1,000, that gives me 15 milliseconds. And if you think of the, reading along, and then you have to do the head swing, and you do the head swing back, and the average access time on a disk drive now is, roughly 6 milliseconds. So 2 times 6 is 12. We're, pretty close to 15 is pretty close to 12. We're doing okay. So the number makes sense. It's what we expect. But you can see for this 10 gig file, if you've got 10,000 writes in it, you're looking at 2 minutes to read it. Not to copy it, just to read it. Read it and shove it in dev/null. So if this is an image for VMware or Parallels or some other file that you're actually going to do a ton of discontiguous writes on, your performance is going to be in the toilet. It really is. So I started investigating further because I hate to actually report something and then have someone come back to me later and say, hey, you didn't do this one really simple thing. It's only in your test case that it's failing. So what about if you do this? So the first thing I did was, okay, make sure that there's no effect on SSDs. And there isn't. The access time on SSDs is in the order of microseconds. You're basically just going to a different part of the flash chip. There's nothing to move, of course. So that's why APFS is so wonderful on flash media. But we sell a lot of storage to video and to film and entertainment. We have a lot of customers who have terabytes of stock footage online. They're photographers. They're running databases. They have lots of high storage needs, and these people are still on rotating disks. The rotating disks, there's a sweet spot. $400 will buy you not the latest and greatest, but 6 months later, older than the latest and greatest. So $400 buys you what, a 10 or 12 terabyte drive now. So for that, there's no way you can touch that in solid state, and the longevity, the risk of degradation is much lower on hard disks. So the next thing I did was I looked at different types of hard disks. I looked at enterprise versus consumer. I thought, well, maybe it's just consumer drives. So I looked at enterprise drives. Sure enough, they're faster, but they still have the same effect. And then I thought, okay, maybe it's just 10 gig files. Maybe, what they said is right. Maybe a 100 meg file is going to be fine. A 1 gig file is going to be fine. So I did different file sizes, and what I found was, lo and behold, it's still the same, even with a 10 megabyte file. So this 10 megabyte file takes roughly a little bit less than 1/8 of a second to read. As soon as you've got 2,000 writes in it, it takes 3 seconds to read. So 3 seconds for a 10 megabyte file works out to be 3 megabytes a second, right? So 3 megabytes a second from an array that will do 800 megabytes a second. Does that sound acceptable? Okay. So I'm still hoping that we'll get a resolution. At the end of doing all this testing, I want to make sure that I've done everything right. I start looking around, and I don't know if you can read this, but there's a disk-util command that allows you to enable automatic defragmentation. And of course, I discovered this after 5 days of testing and investigation. I thought, oh my God, I'm going to have to do all this testing again. And I was really not liking the world at that point. And then I started playing around with it. You can turn it on, you can turn it off. It's supposed to work in the background. As far as I can see, it doesn't do anything. It doesn't, really. I thought, well, maybe you have to remount. Maybe it needs an hour of idle time. Maybe, I tried all sorts of things. I could not get it to unfragment my one 10 megabyte file on this volume to save my life. And then I tried it with 100 meg and then with 1 gig, and literally it was not doing anything. So hopefully in the future, either Apple will give us a way to turn it off, or they'll figure out the defragmentation such that it's usable. At this point, we have customers. So we've been shipping a beta of Software 6, which supports APFS for many months. We have customers who have figured out by themselves that things get slow with APFS, and their solution is to copy their 40 gigabyte VMware or Parallels image off onto another volume and copy it back. They do that once a week, and they maintain halfway decent performance. But that doesn't sound like a real solution to me. So on a more positive note, let's start talking about some of the cool things about APFS and how APFS solves some really basic problems with file systems. In particular, APFS has a pretty cool way of allocating space and a really interesting way of organizing files. And we'll go through those one by one. So the first thing you need to know about file systems is that file systems store everything on blocks. The block is like a quanta. They can't store less than a block. They can store multiple blocks. In the case of HFS, up to 17 terabyte volumes, the block size is 4K. For APFS, it's also 4K. The blocks are numbered. They start at 0. You know, it's basic computer science stuff. So for HFS, the blocks all get, whether a block is in use or not, is kept track of by this data structure called an allocation bitmap. And the allocation bitmap is just byte for byte. If there's a 0 there, it means the block is free. You can use it. The file systems say, yeah, I'm going to use it. They put some 1 there. It's in use. And it just maps 1 for 1. And these things go on and on and on for in size. In particular, with HFS, a 14 terabyte volume is going to be over 400 megabytes in size. Okay, a 17 terabyte one works out to be more than 500 megabytes in size. And we have solutions now. We have a 6-drive enclosure. We see people putting together multiple 4-drive enclosures. They're making these 60, 70, 80, 100 terabyte volumes. This bitmap gets huge. Okay, it's the other problem is so if you imagine having 4 disks, each of which has 400 megabytes of allocation bitmap, you're not going to sit around with 2 gigabytes of RAM holding this bitmap for when you need to allocate space. No, what the file system does instead is it reads a chunk and says, can I find this free space? And if it does, it writes, it says, yeah, I'm going to grab that free space. And if not, it has to go read the next chunk. And I found this out the hard way when I'm a firm believer in the old expression, eat your own dog food. So for the last 4 years, or 5 years actually, I've been running a RAID 5 volume on 4 SSDs. And recently, like as I was preparing this talk, maybe a month before, my volume got really, really slow. And I thought, oh my God, one of my SSDs is starting to die. And then I realized I only had 15 gigabytes free on the disk. So what was happening is every time I had to allocate space for a new email message, for an extension to my system.log file, for anything, the file system had to go read. Oh, I can't find any free space. I can't find any free space. I can't find. Oh, I found some. And then it would go back to the beginning and start again, you know? And this was happening over and over and over again. So even on my small 1 terabyte volume, on SSDs, the performance was going through the toilet because it was having to do all these reads for every single write I wanted to do. So APFS has this really cool, clever way of getting around this problem. And all they've done, they're still using allocation bitmap. All they've done is they put this data structure between the code that's asking for free space and the allocation bitmap. And all this structure does is it keeps track of how many free blocks are in that 1K part of the allocation bitmap. So as you go and search through the allocation bitmap, instead of having to read all 1K, you just read this one structure. And if the value is 0, if there are no free blocks in that, you skip it and go on to the next one. And all these structures are in a contiguous array, so they're really fast to search. So you can find free space. You can have 10 gigs left on your volume and of your 15 terabyte volume, and you're still going to find the free space, and it's going to be found much, much more quickly. The other thing that they do, which is really cool, is they don't allocate the bitmaps until they're needed. So when you first create a volume, all you're going to do is create these records and no allocation bitmap at all. So if you've ever made like a 60 terabyte volume with rotating media on HDDs, you see the disk lights, they're on for a while, right? And all they're doing is they're writing out zeros. They're writing out this allocation bitmap. If you do the same thing with APFS, it doesn't have to do that. All it does is it writes these little records saying, hey, I don't need the space yet, but I have this full space is allocated, is ready for you if you need it. And the first time you need to allocate into that block, it allocates that 4K block for a bitmap and starts using it. So it makes the volume creation really, really fast, which I love because people are always saying, why is it taking so long to make my volume? Well, you're making a 100 terabyte volume. What do you expect? So with APFS, I don't have to say that anymore because a 100 terabyte volume you can create in literally a couple seconds. I think it's really cool. I love ingenious solutions. I think this is an ingenious solution. So let's go on to the next thing that APFS does differently, which is how does it organize files? This is often called the catalog. You've heard people talk about a file system catalog. So we're going to go into file system catalogs and how they're organized on disks. You can think of a file system really as nothing but a giant database, right? You need to keep, you give the file system the parent directory and the file name, and it comes back with not only the modification date and the creation date and all the finder attributes and all the other stuff, it comes back also with your data. And your data is just another part of what's in the database. So it's got to keep track of all this stuff based on the parent directory and the file name. And like all good databases, it uses a B tree. And I used to think a B tree stands for binary tree. In researching this talk, I found out it's not. It's invented by a guy named Bayer at Boeing, and he called it a balance tree, so it's either Bayer, Boeing, or balance. That's the B stand for. I couldn't find anyone who would give me a concrete answer as to which it is. In file systems, the block of information, remember I said everything in a file system has to be one block, so all these structures are one block in size, 4K. And a B tree record, so B trees are trees, and in each place you have records, and the records have in them some key you're looking for and a pointer or an address where you're going to get that information. And when you start searching through the tree, what you're going to do is you're going to look and see whether what you're searching for is less than or equal to what's in that record that you're searching. So we have here a simple B tree with 8 names. I don't know if you can read the names. But you can go through the tree and you can just sort of like traverse it. And I'm going to give you an example. The example is, how do we find Neil? So we're going to start looking for Neil. And we're going to say, is Neil I always get it confused. Is Neil less than or equal to Mark? No, it's not. Is Neil less than or equal to Renee? Yes, it is. We go down the next layer in the tree, and we get the next record, and we say, is Neil less than Nina? Yes, it is. So we take that branch, and we go, is Neil, then we find Neil's information, and we have Neil's, his birthday and everything else in this record about Neil. So file systems are exactly the same. They work the same way. With HFS, what we have is we have these, remember 4K? We have this 4K block, which has in it parent directory and file name, and then it also has this block number as the last field. And the block numbers, because that field was set back in 30 years ago to be a 32-bit number, that's the limit on number of blocks you can have in a HFS file system. So every time you want to traverse down a layer in the file system, we just start going down this tree and we traverse it and we say, find the record that's less than or equal to, find that block, read that block, go through that record, do the same thing, just like we did with our other example. So we'll search through the record, we'll find the record we want. The number is 24, we go read block 24. We've done 2 reads at this point, the first one in the block 24. Then we go and search through that record, we find the record we're looking for, it's block 60 is what's pointed to. We read block 60, we go through that, we read block 98, and we have the information. 3 reads, we've got the information we're looking for. So what we find when we start looking at file systems that people have, even with like 1 to 10 million files, is the B tree is rarely more than 6 layers deep. So every time you want to go read, like find a file in a directory, it's going to take you no more than 6 reads to find that file, which is pretty impressive considering how many files you can have on a volume. With APFS, it's a little different, and the reason it's different is they don't actually have a block ID, they have an object ID. And the object ID is just this identifier that tells that, hey, I'm looking for this object. And every time they want to go and look for the actual block ID, they have to go into a whole separate B tree on the side and search through that B tree and get the block ID for the ID they're looking for. So the problem with that is, so we're going to go looking, we're going to do the same exact thing we were doing with HFS. We're going to go looking for a record. We match our record. We get our object number. And then we have to go into the separate B tree and look up and get the block number. And we read the block number. And then we repeat. We go and read that block. We go read through that block, finding the object ID we're looking for the next block. We go through our object ID tree on the side. And so you'll see that every time we do one layer in the tree, we're actually having to search this entire other tree. So what this means is that instead of doing 6 reads to go through traverse one layer of a directory or find an object in a directory, we're now often doing 30. So again, on SSDs, it's no big deal, but on rotating media, it can really be a hit. So eventually you finally get to the record you're looking for, there is some really cool things about this that I'll go into later. This is the slide I showed last year. It is one of the things I did in testing APFS to just sort of figure out how APFS performance compared to HFS performance. It's an install of 1013. All I did was install it on one RAID volume, copy it to another RAID volume, time how long it took. So that, as you can see, it's slower even on SSDs. It's slower even on that device that's got 4 blades all rated together that'll do 2 gigs a second. It's still 20% slower. And it's 20% slower because it's doing all these extra reads. But there is a silver lining to this whole story, and that is that Apple is using this as a way of doing snapshots. And this, I think, is really cool technology, and I love it, and I gladly put up with slower copy speeds for this. So the way it works is if you think of the very bottom of this tree where we're actually getting information about the block number in the object ID lookup table, the object ID B tree, then what is in there is not only the object ID, but also a transaction ID. And the transaction ID is just a 64-bit number that keeps growing every time the file system does an operation. And in Apple's documentation, they said if you do, I think they said 5,000 writes per second to a volume, it takes like 150 years before that number rolls over. So they're pretty confident that it's not going to get corrupted because the transaction ID is going to roll over. So the cool thing is that, so as you start using, doing any modifications to your file, your transaction ID gets updated in this record. And then if you want to go and take a snapshot, instead of having to do anything, all you do is you create the snapshot record and store the current transaction ID. I think this is so magic because anyone who's played around snapshots knows they're fast. Even you can have a huge volume and they're super fast. And this is why all they have to do is store this one 64-bit number, a little bit of information about the date, maybe some information about a name. That's it. They're done. Then what happens is after this, if you go and do a subsequent write, the file system knows that this volume has a snapshot on it. And so it adds a second entry in this B tree, and the second entry is just the same object ID with a different transaction ID. So now we have 2 entries with the same object ID, the different transaction IDs, and each one of those points to a different place on disk, a different block. So one points to one block that has information about the file beforehand, before the snapshot, and one points to the file as it is now. So if you want to go and read the file as it is now, you just go looking through this thing. You found your object ID, in this case is 21, and you just find the largest transaction ID. So this thing is sorted first by object ID, then by transaction ID. So you just search through until you find the last record, the last little record in this structure that has the largest the last one with the object ID you're looking for, and that is the latest file. If you want to find the file from the snapshot, so our snapshot ID is 601, we're looking for an object which is less than or equal to 601, and this first one is 480, the second one is 654. Obviously, the second one isn't what we're looking for, the first one is what we're looking for, and that's how snapshots work. Isn't that cool? Like one write, and you've got a snapshot. I think it's like magic. I really do. So anyway, let's go on to the T2 chip. I thought I understood how the T2 chip and then worked, and then Marco Young from Oxford University Computer Security sent me an email and said, you know, you almost have it right, but not really. So I did some more research, and I think I really understand what's going on. And as a background, so we're all on the same page, I'm going to go through really quickly a review of full disk encryption and volume encryption, so we'll all have the same terms. Some of you may know this much better than I do. If I get anything wrong, let me know. So we'll start with full disk encryption from 30 years ago. 30 years ago, full disk encryption meant you type in a password. The password is the key for the encryption. If you want to go and re-encrypt with a different password, you have to go through and decrypt everything and re-encrypt everything. The other problem with using the key as the password is you can take the key beforehand and take some known part of the disk. Like we all know that the first 1K of a HFS volume is zeros. So you can encrypt, you can take like the 10,000 most common passwords, go and encrypt 1K of zeros, come up with this wonderful table with all the passwords and their 1K equivalents, and then anytime someone passes you a disk drive, you can just do the compare and really quickly find the password for your ex-wife's hard drive or whatever it is you want to snoop on. So can you tell I've been divorced? I love my new wife, though. She's great. So anyway, so this is great. So people who are much smarter than me came up with this really cool solution, which is to use what they call media encryption keys. So media encryption key is, in this case, a 256-bit number that is actually the key that you use to encrypt and decrypt your data. But this key is, so by you doing this, you get a whole bunch of great advantages. One, anyone who wants to do a random search has to search all 256 bits worth of information. I can't remember how many gazillion years it takes, but a long time. So if we're going to set a password, what we're going to do is we're going to take this number, we're going to take the user's password, and we're going to encrypt this 256-bit number with the user's password and store that on the hard disk or on the media. So this encrypted key is called a key encrypted key. KEK is what you find whenever you start reading about it. And it just gets stored on the disk or on the flash drive. And then when you want to decrypt it, all you do is everything in reverse. You read it off the media, you take it into your encryption engine, you decrypt it with your password, and now you have your media encryption key, which you're going to store. Media encryption key, remember that term because we're going to use it later. So then when you want to go and do reading your data, you just use the media encryption key, the data comes in, boom, it gets decrypted, out it goes, you can read your file, nobody's the wiser. When you want to change the password, unlike before, it's really easy. All you do is you take your media encryption key, which now is allowing you to read and write data, right, because you've already unlocked your volume, and you encrypt it with your new password and store that on the disk. And after you do that, the next time you want to read your data, all you do is you read your newly encrypted media encryption key, or key encrypted key, you decrypt it, and that becomes your new media encryption key. And if you think about this just a little bit, this is sort of the fundamental way that we get things like multiple passwords, administrative passwords. All these things are implemented in the same way of encrypting a media encryption key with various passwords and storing them. So we're not storing these big long things, we're just storing the same, it's always the same size, it's always, in AES 256 is always 256 bytes, 32 bytes, 256 bits. So it's a known quantity. So if we want to go and securely erase this, all we need to do is generate a random number, store the random number on the disk, and then when we go and try and mount the volume and enter the password, we're going to decrypt this random number with our password and get it up with an invalid key, and then when you go and read, what are you going to get? You're going to get garbage. Great. that's like really fast. You've totally rendered that media completely unreadable, and all you've done is written 32 bytes out there. So the advantage of media encryption keys are you can change the password simply, so you can do secure erase, you have the erase data is fully protected by this huge random number. You can have different passwords on the same disk in different volumes. The disadvantage is, and when you hear about people saying, oh, well, Spectre and Meltdown, for instance, are used to get encryption keys, this is what they're talking about. They're being used to get the media encryption key, because if you have the media encryption key, you can read the data, okay? So that's what people are so worried about when people are talking about snooping on memory. This is one of the targets. So the answer to this is the hard drive manufacturers got together and said, oh, we got a solution. We're just put all this encryption stuff in hardware on the drive. And the drives are called self-encrypting drives. They're sort of, especially after the Sony break-in, where all the movie data got stolen from Sony, that became a really hot topic in the movie and entertainment industry. The way it works is if you've got a disk and you don't actually have a password, it still has a random number. But the random number doesn't get decrypted as you power on the drive, as you mount the volume. All that happens is you just read it off, and this media encryption key goes straight into your hardware decryption engine. So then with no password, you're just going to read data. It's going to be exactly the same as the software way of doing it before. So when you want to add a password to your self-encrypting drive, all you're going to do is exactly the same as changing a password before. You're taking the media encryption key, you're encrypting it, you're storing it on the drive. There are SATA commands for doing this. And we get all the advantages like secure erase and everything else. So let's have a look. So the disadvantage of self-encrypting drives gets us around this whole problem of snooping on memory, but I think it was 6 months ago, someone started writing about this really clever way of getting around this, which is you've got your laptop or your computer, it's asleep, you pull out the drive while maintaining power to the drive, and you plug it into a media reader, and now you can read it because its media encryption key is just sitting there, and it thinks everything's fine, and you just read everything, and you're there. So, and likewise, people are starting to talk about ways of getting M2 drives out of M2 slots while maintaining power. So all of a sudden, this thing that was supposed to be our killer way of solving this problem is even more vulnerable, because you actually don't even have to have malware on there. All you have to have is physical access to it, and it has to be powered on, and you can pull it right out. Even if the volume's is locked, you're still there. So the T2 chip. Apple obviously knows a lot more about this than I am. The people I talk to in Apple Encryption are really smart and really understand these things. So let's go and see what the T2 chip is doing. And Apple has some documentation, which is what Marco pointed me to, and I was trying to wrap my head around it, and I thought, okay, the best way to wrap my head around this is to think of it in terms of the media encryption key, because you need the media encryption key to do your encryption, right? So let's work backwards from the media encryption key into the T2 chip and see how things are handled all the way through. If you start from the other end, like Apple's documentation, you're going to sit there and you're going to fall asleep, believe me. I did last night. So when you want to create a new volume, you're going to ask I think the random number generator is actually in the secure enclave, but I'm not sure. You're going to ask it for a new 256-bit key. It's going to be your media encryption key, right? So it's going to be the thing the encryption engine uses to encrypt and decrypt all your data. Then something really interesting happens. This key gets combined with a media key. And the media key it's not a media encryption key, it's a media key. It's an Apple-specific key. It's in the T2 chip. It's not in secure enclave. It's just sitting there. Doesn't do anything except it implements the remote wipe feature in Find My Mac. So that key has to be there. If that key changes, then when you end up with bringing in your other key and mixing the two, you're going to get the wrong media encryption key, right? So that sort of happens before it gets to the secure enclave. Then when you get to secure enclave, you're going to combine that encrypted key with the user's password, or no password if they don't have a password, and the hardware ID that you've heard Apple talk about with their secure enclave. And that combination, the doubly encrypted mixed with the user's password, is what gets stored in the secure enclave. So this is like a much more complicated way of writing your key encrypted key on your disk in a secure self-encrypting drive. Likewise, if you're going to mount a volume, it's just the whole process in reverse. We pull it out of the T2 chip. We ask the user for the password. The hardware ID gets added to the password to decrypt that stored key. It comes out, and it then gets a second sort of level of decryption with the media key, and that result gets stuck into the hardware decryption engine that gets used to decrypt all your data. So that's how you get your media encryption key back. So what happens when you want to secure erase a volume? Because APFS is set up where each volume and the container all have separate keys, we can just go and nuke one of the volume keys in the secure enclave, and then we won't be able to we won't be able to read anything, because when we go and enter the password and everything, we're going to get the invalid key. It's going to get decrypted with the media key. You're going to have this invalid key sitting in your list of media encryption keys for the hardware that's going to do decryption. And when you do your decryption, you're going to get garbage out the end. So likewise, if I do secure remote wipe and I nuke the media key and put random data in that, then everything on that piece of hardware is toast. Even if I can get it out, it's toast, right? Because now no matter what I put through, it's going to get mixed with garbage. Even if it's a simple XOR or something, it's going to get mixed with garbage, and what comes out at the end is going to be garbage that you won't be able to decrypt anything on that piece of hardware. I thought this was pretty cool too. I was pretty impressed. So the major advantages we have here are we have all the advantages of the self-encrypting drives without any of the disadvantages. We don't have the problem with only one password on the device. We don't have the problem with, hey, I can remove power, because the hardware ID is different on each Mac, so you can't take this drive out and plug it into another iMac and start snooping on it, right? Because that hardware ID is different on each Mac. It turns out there's something even more interesting happening, and I think they're using the media key for this. If you take an iMac Pro and you take storage out of it, and you put in other storage, and you power it off, and then you take the second storage out and put the original storage back in, you can't read it. So I think what's happening is that every time the T2 chip sees a new serial number in the flash memory, it generates a new media key. So I know this is, I heard this from Mike Cobb at Drive Servers, and I trust what he says. So I think it's really interesting. I think they're really trying to have some concrete ways of mitigating some of these hardware attacks against computers. So lastly, what I want to do is I want to talk about how people lose data on volumes. So the last year and the year before, I was talking about disk drives and how we predict disk drive failure and what the frequencies are and all this stuff. And someone came up to me at the last conference I was at and said, so how often do people lose volumes because of disk drive failure? And I thought, hey, I've been talking about disk drive failure for so long, but I'm missing one of the key points, which is people don't really care how often their drives fail. They care when they lose data, right? So let's start talking about that. Some of you will have seen this before. This is Serena Catania. She used to be a head executive vice president level at MGM and United Artists. She then decided to start her own business doing documentary films. And she called me in tears just before NAB 2016, and I'll let her describe exactly what happened.
On the 14th of April, 2016,
do we have audio?
I was organizing media, copying originals, moving things into new folders, and streamlining everything. So I had both the originals and the copies attached. There was over 100 terabytes there, 4 24 terabyte RAIDs plus other hard drives. I unmounted everything and left to go to the airport to drop a friend off. And when I came back a couple hours later, brought the computer out of sleep, and every single RAID had been crushed into smaller partitions, and there were 0 terabytes on everything. It showed 0 terabytes. So I had the equivalent of 200 laptops basically erased from the time I left until the time I got back. It's 5 months later, and my company is still reeling from the effects of that.
So we're now 2.5 years later. This is what she saw when she came back, by the way. So she had hardware RAIDs, she had G RAIDs, she had Drobos, she had individual disks, she had many soft RAID volumes. Every single physical device got reinitialized and labeled as a MyBook. If you go Googling around, you'll find the culprit for this. I'm not going to name names, but so this is the reason I bring this up is for 2 reasons. One, it's 2.5 years later. Several of her projects, she only had all the copies of media, of footage she had shot over 10 years were on these drives. Why did she have them all online? Well, she was doing the right thing. She was making sure she was fully backed up. Her mistake was she left her computer, put it to sleep with her backups and her regular drives all attached at the same time. So we're in this RAID business. We do really good tech support. Mark James, the guy who I've been working with for almost 30 years, comes to me every time we have a user who's lost a volume, and oftentimes, especially with volumes being so big, people don't have backups. They know they should, but they don't. And so what I want to do is sort of go through, quickly go through the last 10 years of our experience and what we've learned looking at people and how they lose data, and what we've done to help fix the problem and what problems are still remaining. The key thing here is I see so much more data loss caused by software, as in this case. There's some really clever programmer who thought that, if he just hacked the system into this cool thing, that he could automatically initialize disks when their software did something, and unfortunately, he got a little too clever and erased everything. And Serena is not the only person who ran into this problem. So back in 2008, this is sort of what our failure rate looks like. This was pre-RAID 5, so we had RAID 0 volumes. And I don't know if you can see, the frequency I put up here is roughly the number per month. So with a 4-drive RAID 0 volume, with the average industry standard failure rate, say, of 3%, which is not high, not low, it's pretty average. You're going to lose one RAID. You're going to have a 1 in 10 chance or 1 in 8 chance of losing that RAID 0 volume every year. So it's roughly 1 in 100. These are all approximate numbers. We've only just started really doing a rigorous collection of statistics, but these are what we got from going through old support emails and figuring out what our failure rate. So we also had users losing volumes due to user error. They would go into software, they'd click the wrong disk, they'd zero it, they'd certify it, they'd do something else. And it was about 1 in 3,000 per month, which just seems really high. And that made me really uncomfortable that people were using my software to basically destroy their volumes. So in 2010, we introduced this concept called volume safeguards, which is basically a way when you make a new volume, it gets locked so that you can't do anything with the disks that are attached to that volume unless you undo the safeguard. You have to enter your admin password to undo the safeguard. And that actually, it seems really simple, right? But it actually took this problem that was 1 in 3,000 and took it down to like 1 in 700,000 per month. I think we've had like 1 or 2 in the last year. So I was pretty happy with that. So fast forward to 2014, we've shipped RAID 5. So our failures from disk drive failure, which were before, what did I say, 1 in 100 per month, are now like practically nothing. So we're going to reset the horizontal axis here, so we're not looking at little tiny slivers on the screen. And what we find now is that less than 1 out of 1.5 million users per month are losing their data from disk drives failing. But there are other things that are happening that are causing people to lose volumes, right? And we should talk about those because they're important. So the first one that was happening the most frequently in 2014 is that periodically with certain users, all of their disks would disappear off the bus and come back 4 seconds later. And I talked to Apple, I sent a bug report, they said, yeah, you don't know what you're talking about. I talked to the head of Thunderbolt at WWDC, he said, oh yeah, we've seen it, it's just dirty connectors, go buy these really expensive swabs and ship them out. So he spent $300 in swabs and little alcohol packets. Every time a customer had the problem, we'd FedEx them an envelope with the stuff in them, they'd like swab the thing and no effect, right? So then we started realizing, oh, it happens not only on Thunderbolt, it also happens on SATA inside the Mac Pro Tower. And I was on a conference call talking about APFS, and I brought this up, and the head of storage at Apple, head of storage software, heard about it and said, oh, we should investigate this. This is just before 10.12 shipped. And so when 10.12 shipped, what happened was when 10.12 shipped, they put in logging so they could watch it. And when 10.12.1 shipped, what happens to the orange bar? It goes almost completely away. Okay, so the reason people were losing volumes is that it's just like when you disconnect a volume that's still mounted, a certain percentage of the time you're going to need disk warrior, and a certain percentage of the time you're just not going to see that volume ever again. So this is exactly what happens. So we still have a little bit of a problem. It turns out that certain combinations of monitors, I think the Apple 4K or 5K monitor was really suspect. Certain combinations of monitors and docks, if they're plugged in, will cause all the devices to disappear. And our solution now is just tell people, okay, put your storage on a separate bus, or change your configuration. And we've been able to get people to get around this problem just by changing configuration. So let's talk about the next two problems, the red and the magenta one. So it turns out that a certain frequency, 1 in 4,000 a month, what's happening is, you know that like each physical disk has a BSD disk number, right? Disk 2 is this disk drive, disk 3 is this disk drive. It turns out at a certain frequency, the kernel gets confused. And when you send I/O to this disk 2, it actually goes over to this drive, and disk 3 goes to this drive. And you can imagine what happens, right? You get corrupted volumes, you lose data, people get pissed off. I always think that it's my fault, so I go looking through the code, and I spent like several months looking through the code. And then we finally had a customer with a Thunderbird 4 independent drives, all of them initialized with Apple Disk Utility, had HFS volumes, 4 independent HFS volumes. He then took software, and software has a feature which allows you to certify a drive, which is destructively testing a drive. So he had 2 volumes mounted on 2 of the drives, and certified the other 2. Well, you know that you can't get write access to a drive with a mounted volume on it, right? You can't write to it. So it was writing to the other 2 drives, and then at the end of the process, the next day he comes and he restarts, and his 2 mounted volumes are trashed. And that told me, because the software driver wasn't even loaded, that it wasn't my fault. It wasn't my driver. So what's happening is somewhere in the kernel, there's this bug that's causing these devices to get swapped. And of course, I submitted a bug report, and of course, I got the same type of response I got with the first bug, which is Apple says, you don't know what you're talking about. It can't possibly be happening. So what I did was I put into 5.7, which shipped in software 5.7, which shipped in October. I put in code that detects when this event happens, and all I do is I write lock the volume at that point. So the volume that you can't write to it, you have to restart. And since we put that in, we've had 0 people report that they've lost a volume due to this bug. So we can't fix it, but I can detect it and keep people from losing data. And that makes me really happy. I hope that someday I'll get Apple to fix it, but So a lot of these problems, what you'll see is a lot of these problems aren't our problems, but we're still investigating them, because my goal is to give people, used to be give people the fastest storage possible. Now it's to give them the most reliable storage possible and also make it really fast. So let's talk a little bit about this last category, the magenta category, 1 in 10,000 a month. What this is it turns out we see when people do system upgrades or install a new driver of any type, when they reboot, often they lose their volume. This started happening only when people started booting from SSDs. And my hypothesis has been that because SSDs will allow you to reboot so much more quickly, that there was data, and disk drives now have huge RAM caches, right? They've got a 1/4 gigabyte. And if you do the math and say, okay, how long is it going to take me to flush that 1/4 gigabyte out to disk? Say that's stale, it could take quite a while. And if your drive goes down really quickly, your computer goes down really quickly, it might not have, and power goes off when the computer goes down, then all that stuff that's in the DRAM cache might be lost. So I put code into Sofray that added a 5-second pause at shutdown restart. It unfortunately has not fixed the problem. So there's another problem going on. Part of what was going on years ago was Apple would send a synchronized cache command, i.e. flush everything out of DRAM onto the media command to the Sofray driver, and then it would send another 75 writes. And which makes there's a command saying, hey, I'm done. You shouldn't be doing anything after that. And I sent a bug report to Apple on that, and they said, oh, you don't know what you're talking about. And 3 years later, I was talking to them, and they said, oh yeah, we finally found that what you were saying was true because we found it with the Mac Pro, 2013 Mac Pro, when we started using NVMe storage. So eventually they figured it out, but we still need to figure out how to get around this problem. This is one of the key places where I think APFS is going to help, because you won't lose the volume, you'll just lose everything you've done in the last 5 seconds. So, it's better than nothing, right? So the two things that I want to mention, which are really interesting, going back to the original question the person had at the conference, is how often do people lose data due to disk drive failure? We have not seen anyone lose data due to a disk drive failure on a RAID 5 volume. And the sort of urban lore is you need RAID 6 because with RAID 5, you can lose that second drive while you're doing a rebuild, and all health, you're going to lose all your data. It's true, it's technically possible. We just have never seen it. We have over 100,000 disk drives in the field using Sofray, and we have not seen this, ever. So we're going to do RAID 6. RAID 6 and RAID 6 are going to be in Sofray 6, which will be out in the spring, in the early spring. We're doing it because people want that level of reassurance, but I just don't see it being, I'm waiting to hear from someone who's had this happen. If it's happened to you, let me know. If it's happened to you, okay, I want to talk to you. The other thing we don't see is bit rot. People are saying, hey, there's a problem with bit rot. Things happen on media. Data gets corrupted, and we're not seeing that we see it with flash media on the little thumb drives, but not on these. Lastly, I'd like to thank the two people who helped me incredibly in this preparing for this talk. One is Rick Rockhold. He now works for OWC. He's the guy who reverse engineered APFS. Took him about a year to do it. He's the author of MacDrive, the program that allows you to mount a Mac volume on a Windows machine. He and his team are also doing Sofray for Windows. The other person is Mike Cobb from Drive Savers, who gave me a deep dive on the T2 chip. Thank you.